So this is going to be our last like regular lecture video. So there will be one more video that I'll post either Friday or Saturday about just going over some questions from the review. So if you haven't already, I posted the review as well as the solutions. So you can look through that. Just even if you don't have the chance to actually go through everything, if you can just pick out a few questions that you think that you'll have questions about, then even that would be useful to help me figure out what questions to go over in my next video. So today we're going to be talking a little bit more about diagonalization. So I want to do one more kind of full example together, just going through diagonalizing a matrix. But other than that, we're just going to talk a little bit about like stuff that's a little bit more theoretical related to this, like basically a kind of light proof of why diagonalization works, as well as some other kind of facts about diagonalization. So I think even after yesterday's video, honestly, I think you have all the tools you need to do the online homework. I don't think there's really going to be anything today that like you absolutely need to know. But that being said, I think it will help kind of fill out your understanding of diagonalization. And so for that reason, I'm not going to actually make another worksheet for today, just because I just don't think there's really much that I would put on it beyond, I think if you did the worksheet from yesterday, you've done plenty of practice with diagonalizing, and we're going to go through another example together now. So I just don't really think it makes sense to give you more of that. Okay, so this is still section 5.3 in the book. Diagonalization. Okay, so as we talked about last time, a matrix is called, so an n by n matrix A is called diagonalizable if it can be written as A is equal to P D P inverse for a diagonal matrix D and an invertible matrix P. So this is like the general definition, but how is this actually going to work? Well, if it's diagonalizable, this diagonal matrix isn't just going to be some random diagonal matrix. It's actually going to be a matrix containing all of the eigenvalues of your original matrix. And then the matrix P is going to contain all the eigenvectors. So let me write that stuff down, and then we'll do an example, and then what we'll come back to is seeing like why this works the way it does. So A is diagonalizable if it has n linearly independent eigenvectors and if that's the case, your matrix P is going to be those linearly independent eigenvectors as the columns. And then your diagonal matrix is going to be a matrix where the diagonal entries are the eigenvalues that correspond to those same eigenvectors put in the appropriate order. Did the same thing last time, I think. Always underestimating my matrix size that I'll need. And then I'm just writing zeros there as shorthand to say that there's zeros everywhere else. It's not like there's actually two big zeros. Every other entry is a zero. Okay, so let's go through an example of this. So we're going to diagonalize the matrix. Let's see, 4, 2, 0, 0, 5, 0, -2, 4, 5. So basically, we're just going to kind of along the way figure out whether it is actually diagonalizable. So we're going to find the eigenvalues, find the eigenvectors, and then if it turns out that we don't have enough linearly independent eigenvectors, then it's not diagonalizable. If we do, then that gives us our matrix P, and our eigenvalues give us our matrix D. So let's find the eigenvalues. So first step is going to be find the eigenvalues. So the way we're going to do that is we're going to find the determinant, or set the determinant of our matrix minus lambda times the identity, set that equal to 0, and solve for lambda. So if we take our original matrix and subtract lambda from the diagonal entries, we're going to end up with 4 minus lambda, 0, -2, 2, 5 minus lambda, 4, and then 0, 0, and 5 minus lambda. So to take this determinant, we can pick any row or column to expand through. Definitely makes most sense to expand through the third row in this case. So if you go through and do the determinant, you're going to get 0 times something plus 0 times something else, and then the only thing we're left with is 5 minus lambda times the determinant of the remaining matrix, which would be 4 minus lambda, 0, 2, 5 minus lambda. And so that's going to give us 5 minus lambda times 4 minus lambda times 5 minus lambda, because when you take the determinant of this smaller matrix, the 2 and the 0 just give you 0. Okay, so now we're going to set that equal to 0. So we have 5 minus lambda squared is equal to 0. Oh, sorry, I forgot about the other part. 5 minus lambda times 4 minus lambda is equal to 0. And so that tells us that our eigenvalues are lambda is equal to 5, and that one has multiplicity 2. And then we also have lambda is equal to 4, and that one has multiplicity 1. Okay, so now that we have our eigenvalues, now we can find the eigenvectors. And so this is where we are now going to be solving an equation, a matrix equation. Find the eigenvectors. So in this case, we're now going to be solving, this is what I wrote wrong last time, a minus lambda I times x is equal to 0 for each of our lambdas. So let's start with lambda is equal to, what order did I do it here? Let's start with actually the second one. So let's make lambda 1 equal 4. So if we do a minus lambda I, so going back up here, our original matrix A looked like this. So maybe I should have rewritten it down there, but look at it, make a picture in your mind. So we're subtracting lambda, in this case, we're looking at 4, so we're subtracting 4 from each of the diagonal entries. So if we do that, we're going to get, let's see, where did I write that down? Can't keep track of my own work. So I think that's this one. I think that's, sorry. I thought I had it written down, but I'm just going to scroll back up. So that's 0, 0, -2. And then 2, 1, 4, 0, 0, 1. Okay, I did have it written down. Okay, so we're trying to figure out, we're going to set that equal to 0. So we're solving 0, 0, negative 2, 2, 1, 4, 0, 0, 1. We're solving that times x equals 0. And so how can we do that? We can do it with an augmented matrix. So I don't want to actually go through together the process of reducing that because I think that's something that you all have a handle on by now. So if you take that matrix and reduce it, you should find that it reduces to the following: 2, 1, 0, 0. So there's some rearranging of rows going on here. So what does this tell us? So if we look at our columns, we see that the second column is not a pivot column. So that means that x2 is a free variable. So we can either say equals free or that it just equals x2. If we look at x3, we have x3, 1 times x3 is equal to 0. And so that tells us that x3 is equal to 0. And then if we look at x1, we can work out that x1 is going to be equal to negative 1/2 times x2. And so putting this all together, we figure out that our vector x from our original equation should be equal to negative 1/2 x2, x2, and 0. And so that's the same thing as x2 times negative 1/2, 1, 0. So this tells us that our a basis for our eigenspace, the eigenspace corresponding to this particular eigenvalue, would be the vector negative 1/2, 1, 0. What we can do instead is, or what we can do is we can take that vector and scale it just to make it so it doesn't have fractions in it. You might as well. So let's make our first eigenvector is going to be v1 is equal to, and let's see, how did I do it here? I multiplied everything by just by 2. So I left the first entry negative, and I just multiplied everything by 2. So that would give us negative 1, 2, and 0. So that is our first eigenvector. And again, other answers would work. You could have done negative 1/2, 1, 0. You could have done any multiple of negative 1, 2, 0. But you might as well choose whatever's like the simplest version so that you, when you go and put together your matrix, you don't have as much, large numbers to deal with. Okay, so let's now work with our second eigenvalues. So that's going to be our lambda 2 and our lambda 3. Those are both going to be the second eigenvalue, which was 5. So if we do our a minus 5i in this case, so in this case we're going to get negative 1, 0, negative 2, 2, 0, 4, and then 0, 0, 0. And so we're trying to solve this matrix times x is equal to 0, so that means we can write down an augmented matrix and reduce that. So our augmented matrix would be negative 1, 0, negative 2. And by the way, when you're working with a homogeneous system of equations, which is what this one is, right, because it's equal to 0, you don't have to make an augmented matrix because that extra column is just going to keep being 0. But personally, for whatever reason, I just feel like I can see this, I can like read the solutions off a little bit better when it's in that augmented matrix form. So that's why I still do it, even though it's not completely necessary. So that matrix is going to reduce to, let's see, 1, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0. And so in this case, now we have two free variables, right? Because there is no pivot in columns 2 or 3. And so that tells us that x2 is a free variable and x3 is also a free variable. And then x1 is going to equal -2 x3. And so if we put this together, we get our answer x is going to be equal to, oops, I'll write like this first, -2 x3, x2, and x3. And so if we pull out the x2, we'll get 0, 1, 0. And then if we pull out the x3, we get -2, 0, 1. And so that tells us that the basis for this eigenspace consists of these two vectors, 0, 1, 0 and -2, 0, 1. So those two vectors are linearly independent from each other, right? So those are going to be our two other eigenvectors. They're not the only two answers. You could scale either one of them. If you could come up with two different linear combinations of them that were, linearly independent, that would also work. But again, might as well go with what we already have right in front of us. So we can make our second vector. Just want to make sure I'm being consistent with how I did it in my notes, because there's multiple ways to do it, but when we're doing the diagonalization, you do have to find the inverse, and so the inverse is going to change if you change your original matrix. Okay, so now we can put this all together, and I know I probably should have set this up in a way that you could kind of see all the work as we went. But so we have our eigenvectors are here. We have our second and our third, and then here's our first one. So that's going to give us our matrix P. So our matrix P is going to be, so that first one that I just scrolled past was, I believe, -1, 2, 0. So that's our first column. Our second column is going to be 0, 1, 0. And our third column is going to be -2, 0, 1. Actually, maybe for the sake of not having to rewrite this, so I'll write it below. So this is P, and what are we coming up with? We're coming up with how can you express A as P, D, P inverse. So then the middle matrix D, that's going to come from our eigenvalues. So because our eigenvalues are 5 and 4, and then we have to keep track of the order we did them in. So the way that we did our eigenvectors, we're going to put the eigenvalue of 4 as our first one. So 4, 0, 0, 0, 5, 0, 0, 0, 5. And then I'm just going to tell you, I'm going to avoid doing what I did last time. I'm not going to calculate the inverse on screen. This one I did look up ahead of time. So I was kind of surprised by this, but this inverse actually looks almost exactly like the original matrix, except for one number is different. I didn't believe it, but it's true. So this is our P inverse, and this is our matrix D. So that is your diagonalization. So just to quickly mention, and this came up if you did the worksheet from the other day, it is possible to have a eigenvalue with a multiplicity of 2, but not to get two different eigenvectors. So I would look at the example, I think it was I can't remember if it was the first or the second example on the worksheet from yesterday, just so you realize that it does happen that even if you have an eigenvalue with a multiplicity of 2, that multiplicity of 2 does not necessarily mean that it has two eigenvectors. It just means that it appears twice in the characteristic polynomial. Okay, so let's get into some other stuff. So basically what I want to do is just talk through why it is that this works. So, why does diagonalization So the kind of premise of diagonalization is that you're writing a matrix A as P, D, P inverse. And so I mentioned this last time, but I just want to write it out again. In order to kind of show you why this works, instead of writing it that way, I'm going to write it the way that I mentioned the other day, which is that if you take this equation A is equal to P, D, P inverse, and you multiply on both sides by P on the right, you'll end up with AP is equal to PD. So in what we're about to do, we're going to show that this part is true, rather than showing the part with the inverse, just because that's a little bit harder to do. We're going to show that that second part is true. Okay, so the way that we've defined these matrices, right, is that the matrix P is supposed to have all of the, actually, maybe even before we do that, let me, I think if we state this first, it might make it come across more easily. So let's think back to what it actually means to have an eigenvalue and an eigenvector. So remember that lambda is an eigenvalue of A with a corresponding eigenvector of V if when you take A and you multiply it with that vector V, you get the same thing as scaling that vector V by lambda. So really important that you know that. I think like we've done so much kind of computation with eigenvalues, and I just hope that you can still kind of go back and remember that that's really what eigenvalues and eigenvectors are. They're vectors that are scaled by a particular amount when you multiply them with the matrix. Okay, so let's kind of keep that in mind. So if our matrix P, we've said the matrix P is supposed to equal all of the different eigenvectors, right? V1, V2, through Vn. And then the matrix D is supposed to have all of these eigenvalues. So lambda 1, lambda 2, through lambda n, and zeros everywhere else. So let's see what happens if we multiply together our matrix A with P. So this is going to go back to the way that we very first learned matrix multiplication. So if you're multiplying a matrix with a vector, you can think of it as taking your matrix and individually multiplying it with each of the column vectors. So I'm going to write something down and then I'll explain what it means. So this might look a little weird. You might think why is there a matrix inside of a matrix? But each of these things, A times V1 or A times V2, those are vectors, right? If you take a matrix and you multiply it with a vector, you get a vector. And this isn't how we typically do it anymore, but it is true that when you multiply a matrix with another matrix, one way you can think of it is as though you're just multiplying the matrix with each column of the second matrix, and those become the columns of your new matrix. So what do you get when you multiply A with each of V1, V2 through Vn? Well, these V1, V2 through Vn, those are our eigenvectors, right? So we know that if you multiply each of the V1 through Vn with A, you're actually going to get lambda 1 times V1. And then as your second column, you'll have lambda 2 times V2, all the way through lambda n times Vn. So let's compare that now. So again, we're trying to compare AP to PD. So this is what AP is equal to. Let's now look at what PD is. So PD is you're multiplying this matrix with all of the columns being your eigenvectors. And you're taking that and you're multiplying it with this diagonal matrix where the diagonal entries are the eigenvalues. So if you take a diagonal matrix and you multiply it with another matrix, what's going to happen is that you're going to get each of the columns of your matrix are going to get scaled by each of these diagonal entries. So I'd encourage you, if you don't buy that, do an example. So take a matrix, multiply it by a diagonal matrix. You'll see that the diagonal entries are each going to scale the columns of your of the matrix you're multiplying it with. So what are you going to get? You're going to get lambda 1 times v1. You're going to get lambda 2 times v2, lambda n times vn. So the point being, you get the same thing either way, right? These are the same. So what did we, it's not letting me change my pen color. That's weird. Uh-oh. I feel like this might be the day where my pen finally stops working. Okay, well, hopefully it's like kind of working. It just won't let me switch colors. And it won't let me erase either. Oh boy. Anyway, so I was going to just point out these two are the same, right? So we basically just showed that AP and PB are the same, which is what we wanted. Okay, so just a couple more things I wanted to say. And now it's, sorry, technical difficulties. This computer has been getting like more work than it has ever gotten before. For some reason, it's not letting me switch to another page. I'm not sure why. So that's okay. I'm just going to have to scroll down. Oh, it's not letting me scroll down either. Oh, man. Let's see what I can figure out. Sorry, everyone. Okay, now it seems to be working. Okay, cool. Let me go to another page. All right, so last thing I wanted to talk about was just a few kind of like a summary of some stuff that we've talked about. And really, again, this stuff you all kind of have like seen play out in the examples we did, but your book kind of lays these out as a theorem, so I thought it was worth at least bringing them up. So one fact that I haven't mentioned yet, but I want to just quickly write down, is that if you have lambda 1, lambda 2, through lambda n, if those are all distinct, meaning they're different from each other, there's no repetition, if those are all distinct eigenvalues of a matrix A, and the vectors v1, v2 through vn are the corresponding eigenvectors, basically the set of eigenvectors is going to be linearly independent. And I'm not going to prove that. There's a proof in the book. It's in section 5.1 if you're interested. It's just kind of a slightly more technical proof than I felt was really worth taking your time with showing you. But I do want to just write it down here. So the way I would at least kind of, one way that you could think about it is that if you have all these different eigenvectors, eigenvalues, those are all describing how certain vectors are scaled. So if you have a certain vector that's being scaled by a particular amount, any other vector that points that same direction is going to be scaled that same amount, right? So we've seen that like anytime you're finding eigenvectors, there's multiple eigenvectors you could pick to go with any one eigenvalue. But if you have two different eigenvalues, there's no way they're going to have an eigenvector that points in the same direction, because eigenvectors that point in the same direction are scaled in the same direction. They're scaled by the same amount. So that's not like a full justification, but at least maybe that gives you some idea of why when you have different scaling amounts, those are scaling vectors that point in different directions. And so therefore, if you take all of those eigenvectors that come from different eigenvalues, that's going to form a linearly independent set. So based on that, that tells us that if a matrix A, an n by n matrix A has n, sorry, wrote the wrong word there, n distinct eigenvalues, so meaning no repetition, no multiplicity 2 happening. So if it has n distinct eigenvalues, then based on what we wrote above, that means that it also has n linearly independent eigenvectors. And so what do we know about a matrix that has linearly independent eigenvectors, n of them? That means it's diagonalizable. So it basically tells us that any matrix where when you find the eigenvalues, you don't get repetitions, you get n of them and you have no repetitions, those type of matrices are always going to be diagonalizable. So that doesn't mean that, we just saw an example earlier today, right, where we had one that did have repetition and it was diagonalizable. So it's not like the only types of matrices that are diagonalizable are the ones with distinct eigenvalues, but if you do have distinct eigenvalues, then it is for sure diagonalizable. So we can describe what happens if not. So if A has repeated eigenvalues, and this next sentence is basically something we've already seen happen. It's just kind of a more formal way of saying that. But basically it is diagonalizable if the sum of the dimensions of its eigenspaces is n. So again, I really think that that's kind of a fancy way of saying something that we actually pretty much already know. So maybe just to show you an example, like the example that we did earlier, we had for lambda equals 4, we had an eigenspace with dimension 1 because the basis for it was only one vector. And then when we did lambda equals 5, we had 2 eigenvectors. We found that the eigenspace was the span of 2 eigenvectors. So the dimension was 2. And so 1 plus 2 gives you 3. Whereas on the example from the worksheet, you had 2 one-dimensional eigenspaces, and that doesn't add up to 3. So that's really all it's saying. It's just saying basically how many, the dimension is the same as the amount of linearly independent eigenvectors that you come up with when you're going through this process. So just kind of a more formal way of saying that. And then the last thing, again, which if you think about it, we already kind of know, is that if you have, so if you have a matrix and it has some eigenvalues and it doesn't matter if they're repeated or not, if you take all of those eigenspaces and all of the bases for those eigenspaces and you take all of those vectors together, you're going to have n linearly independent vectors in Rn. And so that's going to actually give you a basis for Rn. So that in and of itself isn't that surprising. Anytime you have n linearly independent vectors in Rn, it's a basis for Rn. But that has a nice name. It's called the Eigen basis, I believe. Actually, I didn't write that down, and now I'm doubting myself. It might be called, it's either called an eigenbasis or an eigenvector basis. Let's say eigenvector basis. So let me just write that down. So if you take the set of all basis vectors for all eigenspaces of A, is a set of n linearly independent vectors, and therefore it is a basis for Rn called the eigenvector, or maybe just eigenbasis for Rn. And by the way, this last thing, I guess I should have said, this is if A is diagonalizable. So I'll just add that here. Because if it's not diagonalizable, then that means that it doesn't actually have n linearly independent eigenvectors, and so you can't form a basis for Rn out of the eigenvectors. So that's about it. Like I said, I'm not making a worksheet for today just because there isn't really too much more to practice, and I think I'd rather you spend your time starting to think about the final. But yeah, I will be making a video, like I said, so wait, keep an eye out for that. And as always, let me know if you have any questions, and I will see you next time.